Okay, so just to remind you, all right, ready to start? Here we go. So just to remind you, this is when our final exam is. Now I have a location, and this should be consistent with what we said the first week of class and on the syllabus. Is that right? We said Tuesday evening. So that's the same. Nothing's changed. So just reminding you. So if you go to the ASU final exam schedule, they don't have us as one of those common finals on Tuesday. So we're not going by the online final exam schedule. We're going by this, and this is what I told you at the beginning. Okay? Questions about that? So BAC 316, that's a business building. It's way by the south side of campus, by the south of the MU. South of the MU. Any questions or issues with that? 7 p.m. this Tuesday night of finals. Okay, so last time we're talking about we were talking about this pedal and these tires. So let's kind of summarize. So there's the pedal angle measure. You got a question? It's about 2 hours. Yeah. Okay, so there's this initial angle of the pedal, and from the pedal angle, we saw that the tire valve angle was a different angle that came from the pedal angle, and from the tire valve angle, we could get the tire valve position. Okay, everybody ready to start? Okay, I feel like I'm trying to talk over several conversations. Okay, ready to start? Okay, so the tire valve position then comes from the tire valve angle. So that pedal angle is theta, and so then the tire angle is dependent on it, or some function, we'll call it G, some function of that tire valve, of the pedal angle. And then from G, then we can get position, either vertical position, vertical height, or distance to the right of the horizontal diameter, sine or cosine. So this is kind of this is composition, right? Composition of functions, and this was what we were working on. So basically, in general, it looks something like this. We have some function, and what's the output of that function? Which of those three quantities is the output of that function?
Tire valve.
Tire valve position, right? In this case, if it's sine, it'd be vertical height of that tire valve above the horizontal diameter. Okay? What's the argument? So what's going into sine? If we want the tire valve position, then what do we have to put into sine? The tire valve angle measure, right? The tire valve. So whatever that argument is about, that the resulting sine value will be about that same thing. So if the tire valve angle goes into sine, then sine's going to give the height or the vertical position of the tire valve. But this is all based on a different angle, right? So all this stuff about the tire, about the angle of the tire and the position of the tire valve, all comes from some other angle, which is our input angle. Okay, so that's kind of what we're working on. So the question is, how is sine of g theta, based on whatever g is, however we're changing that angle, how does that change then the resulting function? Okay, so let's do some more of that. We've left off with this one here, and we said that. So when the pedal angle is at 0, the tire valve starts pi over 4 clockwise. And so the first thing we said was we wanted to write the tire valve angle and now we're calling that some function of the pedal angle. So it starts pi over 4 clockwise from the pedal angle, and as the pedal angle increases, so does the tire valve. So how can we write, so when we get back to the 3 o'clock position, tire valve is back where it started. So how can we write the angle of the tire valve as a function of the angle of the pedal? So what would give us the angle of the tire valve as a function of the pedal? What would it be? She wants theta minus pi over 4. Do you agree with that? This angle is, she's saying it's always pi over 4 less than whatever the pedal is. That's right. Okay, so what we want to write then is our red function over here is going to be, for the tire valve, T of theta is going to be, we want the vertical distance above the horizontal diameter of the tire valve in radius lengths. We want the vertical distance above the horizontal diameter of that tire valve in radius lengths. So somebody else, what function would that be? Sine will give us the vertical distance above horizontal diameter. And so if we want the vertical distance of the tire valve, then what needs to be the argument of sine? The angle of the tire valve, right, the angle of the tire valve. But our input is this pedal angle, right? So the input's the pedal angle, the argument's the tire valve angle, and that gives us a vertical distance of the tire valve. So is the tire valve ahead or behind of the pedal? Clearly behind, right? How much behind? And how is that seen in our argument angle? How is it seen? How does the argument angle express that the tire valve angle is always pi over 4 behind? No, the argument angle. How is it seen in the expression of the argument angle?
You take the angle of the pedal and then you subtract pi over 4.
Yeah, if we're subtracting, then that angle is going to be less. It's going to lag behind, right, by pi over 4. Makes perfect sense, right? Okay, so pedal graph. So if I want to compare this to, say, the pedal angle, its vertical position, what function would be its vertical position? We'll call that P of theta. So what about the vertical distance above horizontal diameter for the pedal? Just sine of theta. And you also have an image of what that is. Where does it start? Min, midline, or max? Midline, and it goes to the min or the max? Max first, right? So it's going to look like this. It's going to go to the max, and then back to the midline at pi, and then back to the midline at 2 pi, and then keep going, right? So if the tire valve angle is behind by pi over 4, if we're subtracting by pi over 4, then the question becomes, how will that graph differ from the graph of P? So let's put the graph of P up on both of them. So everything you see here is still the graph of P of theta. So we're gonna sweep out that graph. This is the pedal. Everything blue is the pedal. So now if I turn on the red graph, which is the t function, where will it start its cycle? So the p function starts its cycle at 0 and finishes its cycle at 2 pi. So in terms of the angle theta, what angle will the tire valve start its cycle? When does it hit 0? At pi over 4, right? Because it's behind. So some angle pi over 4 of the pedal angle has to go by. And at this point right here, that's when the cycle of the tire valve is going to start, right? And so behind, in terms of increasing theta, how do we envision behind? Is behind further to the right or is behind further to the left? Yeah, it starts later. So think about it, theta increasing like this. First the pedal starts, and then the tire valve starts later, right? So it starts later, which means for a greater angle. Yeah. What's that? It is recording. But I'll just make check. Yes, it is. Okay, so what's the first cycle of T going to look like? Where's it going to be? If the tire valve is coming behind, its angle is lagging, where's its first cycle going to be? Can you imagine it? So let's do it. So I'm going to turn it on now. So it's not going to start. Watch the tire valve. It's not going to start until now. Now it starts, and that's when theta is pi over 4. So now it's making its first cycle. So what you need to see is that that red graph shifted to the right is the tire valve is making its cycle later. It's behind. It's lagging behind the angle of the pedal by pi over 4. And that's why it's to the right, because for increasing theta, it comes after. Doesn't make sense. So we're motivating. So how are we seeing? We're seeing that the reason why when you subtract from the angle, it ends up shifting the graph to the right, because now that new angle is less than the original angle. It lags behind. Okay, so let's change it up. Okay, so now we want when the pedal is at 0, when the pedal angle is 0, means that the tire valve angle, G of theta, equals pi over 6. Now watch, so I'm going to increase so right now when the pedal's at 0, the tire valve's at pi over 6. And so as I increase that pedal angle, so here, what's the pedal angle now? Sorry, I'm trying to get it. What's the pedal angle now? Pi over 2, that's our quarter circle, right? What's the tire valve angle now? Or how could you find it? How could you describe how you would find it? Let's get you guys involved here. You can still give me an answer if you want to save somebody. Trudy, what do you think? What is this angle now for the tire valve? If the pedal's at pi over 2, where's the tire valve? Or how would you find it? You don't have to give me the final answer, just how would you get it? Pi over 2 plus pi over 6. Okay, so what I want you to do is, I first want you to write the function g of theta for this situation, and then write a new t theta, which is the horizontal distance from the vertical diameter and radius lengths of the tire valve. So we're still going to have our pedal function, which is now horizontal distance, and then we'll have the tire valve function, which is horizontal distance of the tire valve. So write out those two functions. Go. Horizontal distance to the right of the vertical diameter in radius lengths of the pedal and of the tire valve. P stands for pedal, T stands for tire valve. So that's how you can remember. Okay, what is P of theta? What is P of theta? Adam. Is Adam here today? Let's see him. Faisal, what's P of theta? Horizontal distance to the right of the vertical diameter. Cosine. And what is T of theta? Alex. What's that? Okay, so what are we talking about? Where's Jimmy? Yeah? If we want the horizontal position or horizontal distance of the tire valve, then the argument has to be the angle of the tire valve, right? And what is that angle? It's theta plus pi over 6. Okay, so cosine, does it start at the min? At 0. Does it start at the min line, or the max? Cosine. Max. Because when the angle's 0, we're at the maximum distance to the right of the vertical diameter. And then it goes at pi over 2. Now we're at the midline, right? We're at the vertical diameter, so we're 0. And then over to the far left is -1. At the bottom, 0, and then back to the beginning at the maximum horizontal distance. So that's our cosine. Let's plot that. Okay, so there's our pedal graph. Okay, so there's our pedal graph. How is the T graph, the valve graph, going to compare to this one? Is it ahead or behind? It's ahead. So for increasing theta, if it's ahead or starting before, then where's its graph going to be? It's going to start earlier, right? It's ahead of it. It's before. So for increasing theta, watch what happens if I turn on. What happened? Do you see it? Right now, theta is at 0. What about the cycle, the first cycle of the tire valve? Where does it start? It already did. Do you see it? It already started. We're at 0, but prior to that is when the tire valve has already gone pi over 6. So it started already. And so where is its graph going to be compared to p of theta? It's before. It's coming before. It's ahead because its angle is greater. You see? Its angle is pi over 6 greater. It's ahead of the pedal. And so ahead, in terms of increasing theta, means to the left. You got to see that red graph as coming before or ahead of cosine. And that is consistent with the angle being greater. The angle is greater. It's ahead of it. It's ahead of it. And on the graph, that means further to the left. It's going to start earlier. Okay, what do you think? Does it make sense? So that's why when you add, it shifts the graph to the left. And when you subtract, it shifts the graph to the right. So let's look at these. So here so generically, sine, so input we know generically can be x. So rather than using theta, we can just use x. Okay, so my axes, I'm showing every black dot on the axes is pi over 2. And so then I'm showing every full value of pi. And then, let's see if we can make those a little brighter. Then I'm showing our 16 key angles along the way. Does that show up better? Can you see the light blue better? Not really. How about green?
A little bit better.
Yeah, green is good. Okay, so we don't want to. The black is for our. So the green is showing the key angles, the 16 key angles on the circle. Okay, in between our top, bottom, left, and right. Okay, so sine x. We know what sine x looks like. So Tell the person next to you, I'm about to graph sine of x plus 3. What are you going to see when you graph sine of x plus 3 and why? Okay, so explain why and what are you going to see. Go. Tell the person next to you. Those are the biggest parentheses I can show, man. Can you see it? It's up there. Yeah, yeah, it's right up there. Okay.
Yeah. Okay.
Okay, Fernando asked a good question that brings up a kind of a cool point. So actually, two graphs. Sine of x plus 3, quantity, and then sine of x plus pi over 3. Not again. All right, so talk about both those. I don't know what's... Okay, so now I got two different ways of adding pi plus 3. Add it to x, add it to the sine. Go, talk about it. Nicole, what do you think? This first one, sine of x plus 3. Can you explain why? Why is it going to move left? And why does plus adding shift it to the left? Because it starts before it. What do you think? It's a greater angle, so it's going to be in front. It's going to be in front, and coming in front means coming before as you move from left to right. Okay? So is that what you thought? So this is coming first. So it's going to start its cycle back here at negative pi over 3, right here. All right, what about the sine of x plus pi over 3? Omar. Where's Omar? Tell me about this one, sine of x plus pi over 3. What's that going to do? Any idea?
It's opposite of this one.
Opposite. What do you mean by opposite?
Like the curve.
Opposite curve. Karen, what do you think?
It's going to be probably like
Up. Pi over 3 up. So sine x gives us a y value, right? And so every y value is then think of every point in that graph. Its y value, we're going to add pi over 3 to it. Up. Pi over 3 is just a little bit greater than 1. So it's about shifted up by 1. Okay, so now we're going to put all this stuff that we're learning together and talk about these transformations of these sine and cosine functions, because when we have real-world situations that are repeating, or what we call cyclical, then we have to figure out how do we transform sine or cosine to model the situation, okay, in the real world. So we're going to kind of start backwards from that. I'm going to give you graphs, and you're going to come up with the equations. All right, so it looks like a mess, but once you get focused on one of the graphs, the others just will disappear in your mind and you'll be fine. So start with the blue one. And the first thing we want to do is the midline, okay? So is the midline moved up or down from, we know it starts, just basic sine or cosine has a midline right there on the x-axis. So we want to do midline first. I'm going to give you the game plan here. So you're going to do these all first for the blue, then for the red, and then we'll do the purple. Let's actually do purple second. All right, so you can just work on the blue and the purple while I take roll. And so the first thing is, for each of these, midline. What's the midline? So the whole graph, is the whole graph shifted up? Is the middle point shifted up? Is it shifted down? And how much? Okay? Then the next thing is amplitude. What was amplitude again? Remember what it was? Yeah, amplitude is midline, how the distance up to the max and then down to the min. And what does that have to do with in terms of circles? It's the radius, and we did that, right? We said if we want to get our vertical or horizontal position actually in terms of the units of the radius, we just take the sine and multiply it by the value of the radius. Sorry about the screen. I don't know what's going on. Okay, next thing. Period. So the period you pull off the graph, and we talked about that. You either go peak to peak or valley to valley, but it's what is it again? It's this interval of input that gives one full cycle of output. The interval of input, and there's many ways to find it for a given graph. From the period, we get this coefficient b. We talked about that. We were going to have to review that, I'm sure, because it's been a week or so. We worked on that. And then finally, so then we're going to decide, do we want it modeled as sine or cosine? Both are always possible. For any given sine or cosine curve, you can always write it both as a sine as a cosine. So at this point is when we want to decide, and then after we decide that, then we ask, is there a phase shift? Sorry about the screen. All right, the phase shift is this adding or subtracting to the input angle to shift it either left or right, okay? So, do the blue first. This up as much as I can. And then do the purple. By any chance, does anybody have a VGA to Thunderbolt adapter? It might be my adapter. By any chance, does someone have one of those? Okay. It might be my adapter that's doing that. Okay, the task, so do you have your task? So work on the blue one first. So what's the goal? Figure out all the parts of it, and then write a function in this form here. Write a function in this form here that will graph that blue function. After you get all these bits and pieces here, get all the individual parts, and then the goal is up there at the top. Write a function in that form that would graph that blue function. And then if you think you got it, then move on to the purple one. Go through each one of these things, and then write the equation that would graph the purple function. And I'm going to, so this is plenty of work for you. I'm going to try to okay, the video from class got messed up, so I'm just going to reproduce kind of the second half of class here where we were given these sinusoidal functions, sine or cosine functions, and we're trying to figure out what the equation is or what the formula is to graph these functions, and we have to put together everything we've learned over the last 2 weeks to do that. So in class I gave you kind of a roadmap for that, and that was first midline, then amplitude. So we're picking all these things off the graph. The find the midline, the amplitude, and then the period. And from the period, we get the value of b. B is this coefficient of our angle and the argument. That comes from the period. And then after that, we're going to decide if we want to apply a sine or cosine curve, because all of these can be done both ways. And then finally, a phase shift, whether we have a horizontal or left or right shift, based on which of these two that we pick, either sine or cosine. So let's do the blue one first. For the blue one, the midline is halfway between the min and the max. The min is -1, the max is 5, so halfway between would be 2. The amplitude then is the distance from the midline up to the max or down to the min, so that's 3. And that's like, if this were circular motion, which we've seen, that would be like the radius of the circle. The period then is the interval of input that would result in one full cycle of output values. So for this blue one, it's easy here to start at 0, and we got a peak there, and so this interval here is where it starts, the output values start over. So we're going peak to peak, and we see that that is 3 pi. Remember to get b, so our argument is b theta or bx, whatever the input. So this is our input. B is the coefficient, and that's a constant. Given a particular graph or equation, that's constant, and this is our changing input. And those together make the argument of either sine or cosine. So I'll just write sine here. In order for sine to have a full period, that argument angle, so that argument is always an angle, that argument angle must transpire 2 pi. It must go through 2 pi in order for sine to give a full cycle. So what we're saying is we're going to take bx and make it equal to 2 pi. Now in terms of the actual input, we know that the period is 3 pi. So we're saying when x changes by 3 pi, we want b times that to be 2 pi, so that sine goes through one full cycle. So b times 3 pi is 2 pi, and b then, solve for b, 2/3. Okay, so b is 2/3. So on this blue one, we'll make life as easy as we can on ourselves, and we notice that this, starting at 0 here, has the exact model of a cosine curve. Cosine starts at the max, then down to the midline, min, midline, max. That's starting at 0. That's exactly what cosine is. So by choosing cosine, we have no phase shift, because it is horizontally. It's exactly how cosine goes, starting at 0. So now we're ready to write this equation, and here's the form up here. So our amplitude is a, so we got 3 cosine. Our value of b we found was 2/3. Generically, our input is x here, and then plus the midline we found was 2. So if this is correct and I turn it on black, it's going to cover up the blue graph perfectly with black, because it should be the exact same function. And it is. So that blue graph, we found its equation, 3 cosine, 2/3 x plus 2. Okay, so let's move on to the purple. And actually with the purple, we'll do it 2 ways. We'll do it as a sine and as a cosine. Alright, so starting again. Again, we're going to do midline, amplitude, period, value of b, sine or cosine, and phase shift. Okay, For the purple one, the midline, we're here at the max is 2.5, and the min is negative 3.5. So if we get halfway between those, you can add them together and divide by 2. You find that the midline is at negative 1/2. Okay, the amplitude then would be from negative 1/2 up to 2.5, and from negative 1/2 down to negative 3.5 or 3. Okay, the period, again, is what interval of input that gives a full cycle of output. So one place we could possibly start here is here at the peak at pi over 2 and see where it comes back to another peak. Well, it comes back to another peak at pi over 2 greater than 4 pi, or 9 pi over 2. So from pi over 2 to 9 pi over 2 is an interval of input of 4 pi. Again, to get b, we're saying that our argument, we want to be 2 pi. What angle of the argument will give us a full cycle of sine or cosine? Always 2 pi. So we know what that period is. We know that the period in terms of x, over 4 pi, we get one full cycle. So that allows us to solve for b. We're asking what value of this constant, when x goes through 4 pi, will result in one full cycle of sine or cosine values. Solving for b, 1/2. Okay, so we're going to do both sine and cosine, so we'll just start with sine here. So for sine, we have to figure out, this is, here's the midline. So first, a sine without the phase shift and everything else being equal would start at the midline. We know that at the 3 o'clock position, the vertical distance above the horizontal diameter is 0, or it starts in the midline. And in the first quarter circle, or up to pi over 2, that vertical distance goes up to the max. So starting here at 0, it's going to go up to the max or something like this. Okay, and then it's going to keep going. Okay, so this is truly sine, but we want this version. So we ask the question, is this the value of the version of the graph that we want? Is this angle ahead or behind this one? So is its angle ahead or behind of this one? Does it come before ours? Does it come before or after the actual value of sine? So for increasing values of theta, it comes before. It starts first. It starts its cycle here. It starts its sine cycle there. I'm sorry, here, at the midline. Okay, so for increasing values of theta, it starts its cycle of sine here, and then a little bit later, then sine actually starts. So for our graph, its argument angle is before or ahead of this, and so therefore it's a greater angle. So for the phase shift, we're going to have we're going to add this much, because the angle of our graph is always this much ahead of the actual sine. So it's a greater angle. So we're going to have plus, and then we see that this is, how much is that? Oh, right there. So the dot is pi over 2. Sorry, I was looking at the wrong thing. So that dot right there, that's our pi over 2, just like this is. So we're going to add pi over 2 to this. Okay, so again, we're ready to set this up as a sine graph, first of all. So it's going to be it's going to be 3 times sine of 1/2. It's going to be x plus pi over 2. This angle is greater, so it's going to be ahead of actual sine, which means it's going to start pi over 2 to the left. Okay, and then plus our negative 1/2. Again, if this is right, and I turn it on black, it'll cover up the purple graph if we're right. Got it, nailed it. So that's that purple graph as a sine function. So what about as a cosine? So as a cosine function, all this stuff is the same. Midline still -1/2, amplitude still 3, period still 4 pi, so that therefore b is still 1/2. But now as a sine, or sorry, as a cosine, so cosine, let's sketch cosine. At 0, we know that cosine starts at the max. So at 0, we're going to start here at the max of 2.5. And it's going to head down like this. Okay, so this would be an actual cosine curve. So then here's where the cycle starts for the one we want. So is that in increasing theta, is that coming before or after actual just cosine by itself? So this cycle is starting after for increasing theta. It's coming later, right? It's coming later. So that's the argument angle is lagging behind the argument angle of just cosine. So that means the angle is less. So we want it minus whatever this is right here. And again, it's lagging by pi/2. So our cosine starts a cycle here at pi/2 later than actual cosine. So its angle is behind. Okay, so we're ready to change this into a cosine function. First change it to cosine, and then b is still 1/2, but now with cosine, the input angle lags behind by pi/2, and the midline is still the same. Again, if we have it right, when I turn on the black, this new graph, it should cover up the pink graph exactly. And it does. So that's that purple graph. This is the cosine version of that purple graph. Okay, and then the last thing I said in class was I was giving some warning about the the tide problem in your homework. And if this is the quantity that you're graphing, the y quantity is anyway, the y quantity that you're graphing is the distance from the shoreline. Distance from the shoreline. So when the distance from the shoreline is, when the tide is at its high point, meaning it's most inland, well, then that distance is going to be the least. So you're going to have your minimum value is going to be during high tide because the distance between the stake and the shoreline is the least. At low tide, the water has receded the most, so that distance, this distance that we're graphing on the y-axis, is going to be the greatest because the shore is going to be furthest away from the stake. And so you'll have your high tide. Ignore these values. I'm just pointing at the axis and as a general reference. So these values don't mean anything for the tide problem. But in general, your greatest distance from the stake will occur at low tide, and your least distance from the stake on the beach will occur at high tide. So just be careful in that problem that you don't confuse high tide for maximum and low tide for minimum when the quantity that we're modeling is the distance of the shore from the stake. Just keep that in mind, that it's always the quantity in question is the distance of the shoreline from the stake. Okay, good luck and see you Friday.